In the theater of modern architectural ambition, skyscrapers are built to project power, economic dominance, and human triumph over gravity. But in the late 1990s, the island of Taiwan conceived a project that bordered on geomechanical madness. To understand the audacity of this vision, one must look at the geography of Taipei. The city sits directly on the Ring of Fire, an area responsible for 90% of the world's earthquakes. Furthermore, Taiwan is the personal playground of Pacific superstorms, enduring typhoons with wind speeds 250 kilometers an hour. Any conventional structural engineer would have told you that building a half-kilometer steel needle in this specific location was a recipe for catastrophe. But the geopolitical drivers were absolute. Taiwan needed a global landmark, a symbol of technological resilience that would announce its presence on the world stage. The engineers had no choice. They had to build the impossible, or watch their national pride collapse into the dust of a seismic fracture.
Not yet. The war began under the ground. When surveyors and geotechnical engineers arrived at the site in the Xinyi district.
The Taipei Basin was not solid bedrock. It was an ancient lake bed filled with hundreds of meters of soft alluvial clays. This soft clay acted like a giant sponge. If a massive static load of 700,000 tons, the ground would simply liquefy and sink, destabilizing the entire structure before the towers could even climb 50 meters into the air.
To make matters worse, deep-bore geological testing revealed active fault lines running uncomfortably close to the foundation site.
If a major earthquake struck, the seismic waves traveling through the soft alluvial soil would amplify, causing a physical phenomenon known as soil liquefaction, transforming the solid ground into a flowing river of mud. The engineers had to anchor the giant tower to the planet's very crust, or risk an instant structural collapse at the first rumble of the Earth. The structural calculations were frozen. The foundation designs were complete, setting the stage for the physical confrontation with the wind. The subterranean battle was won. But above, a silent, fluid dynamic monster was waiting to strike the tower. While geologists fought the mud below, structural engineers had to battle a silent, fluid dynamic monster above, wind vortex shedding. When high-velocity winds hit a flat, square skyscraper face, the air separates, forming swirling low-pressure eddies on the opposite side. These eddies alternate rhythmically, pulling the building from side to side in a violent perpendicular motion. This shaking the skyscraper with increasing frequency, potentially vibrating the steel frame until it snaps. To find a fluid dynamics shield, the team turned to computational fluid dynamics and physical wind tunnel scaling models. At the Boundary Layer Wind Tunnel Laboratories, scale models of Taipei 101 were blasted with artificial storm winds. The engineers redesigned the building's exterior, introducing double-chamfered, stepped corners that physically confuse and break up the wind currents. By shaping the tower like a traditional bamboo stalk, with 8 distinct safety tiers, they reduced the wind forces by 25%. But to survive the ultimate superstorms, they needed an active, internal counterweight. The battle now moved to the steel core. In 1999, the physical assault on Taipei Basin commenced. To anchor the tower to the bedrock, they drilled 380 concrete piles 80 meters deep into the earth, anchoring the structure directly into the solid bedrock. Above the piles, they poured a massive, 5-meter-thick concrete mat, binding the entire foundation into a single, immovable tight band.
The foundation was sealed, grounded, and verified. The base of the tower was now ready to receive the massive steel core.
But a skyscraper cannot survive earthquakes by being completely rigid. Under seismic forces, a rigid structure will absorb all the kinetic energy
until its materials reach their shear limit and shatter. The design demanded a delicate balance of rigidity and flexibility. The engineers constructed a massive structural core consisting of 8 giant steel megacolumns wrapped around a flexible central spine, bound together by heavy outrigger trusses. This setup allowed Taipei 101 to sway and dissipate the destructive kinetic energy of tectonic waves, transforming the giant needle into a flexible willow tree that bends but never breaks. The foundation and steel core were fused, creating an unshakable base. The tower was now ready to face its first real seismic test. By early 2002, the master structural spine was finished. The concrete had dried, the steel was hung, and on March 31, 2002, the structural design was put to a raw, terrifying real-world test. A massive magnitude 6 sending violent seismic waves directly into the half-finished tower of Taipei 101. On the 56th floor, two massive constructions. But below, inside the flexible steel spine of the building, the outrigger trusses did exactly what they were engineered to do, leaving the main core of the tower completely undamaged. With the core proven safe, the team moved to install the crown jewel of their safety system. On the 87th floor, engineers designed a massive, custom-built chamber to Spinatect. It was a monumental mechanical sphere measuring 5.5 meters in diameter, built from 41 individual suspended from 8 high-tensile steel cables. The sphere sat surrounded by heavy hydraulic shock absorbers, ready to absorb the immense kinetic energy. When storm winds pushed the tower to the left, the massive steel heart lagged behind, physically pulling the building back to the right.
Treads. This precise mechanical layout proved that the flexible steel core worked as a perfect thermodynamic spring, dispersing seismic.
The post-earthquake geological audits were finished. The structural frame was locked, and the active mass damper was armed.
On December 31, 2004, Taipei 101 officially opened its doors to the world,
claiming the crown as the tallest building on the planet at 508 text meters. It immediately transformed Taipei's financial landscape. To deliver visitors to the sky, engineers designed the world's fastest passenger elevators, soaring from the ground to the observatory in just 37 seconds.
At the observation deck, visitors from around the globe looked down at the world below, completely disconnected from the typhoons and seismic threats outside.
Architectural critics and structural engineering peer journals, from Architectural Digest to the American Society of Civil Engineers, stood astounded by the design.
The building was celebrated not just for its physical height, but for its pioneering fusion of traditional cultural aesthetics and state-of-the-art structural safety. It became the definitive, soaring symbol of Taiwan's economic and technological ascendance, a beacon of human injuries. But for a structure standing half a kilometer in the sky, the war with nature never ends. To track structural drift, an intricate network of fiber optic sensors and accelerometers is embedded in the megacolumns, tracking structural stress and seismic waves in real time.
The glass facade is subjected to constant hydrostatic and wind pressure. Automated crawlers inspect every seal to prevent microfractures in the panel array.
To protect passengers during rapid vertical descents, engineers regularly calibrate the active pressure regulation systems, mitigating ear discomfort. After every minor tremor, engineers audit the massive outrigger weld joints, utilizing ultrasonic wave scanners to ensure absolute molecular integrity.
In August 2015, Typhoon Soudelor struck Taiwan with devastating fury. Wind speeds peaked at over
Inside the viewing gallery, tourists watched in awe as the giant 660-ton steel pendulum swung by a record-breaking interpenis. In a seismic emergency, the tower is synchronized with Taiwan's early warning network, automatically halting high-speed elevators and sealing gas lines.
The massive structure is equipped with seismic expansion joints, allowing the building to move independently from the plaza floor during tectonic tremors.
Standing as definitive proof that when sharp journalistic vision meets peak engineering, humanity can not only challenge nature, it can rewrite the rules of the planet.